Hello, this is Scott Landau, and this is the Physics 2212 Lab 5 report for the last lab. The introduction. So the purpose of this lab is to use the principles of electricity and magnetism to measure the interaction between a falling bar magnet and a tube of aluminum foil, and then to also model this computationally and compare the experimental results with the computational model's results. And the physics principles used are Faraday's law, Lenz's law, the Biot-Savart law, and then just voltage and circuits traits. And the system in this experiment is defined to be just the bar magnet and an aluminum foil roll. And the surroundings are the rest of the universe. So for the experiment, initially the bar magnet is at rest at the top of a vertically positioned aluminum foil. The north pole of the magnet is facing the ground, and the tube's inner radius is 2 centimeters, the thickness is 0.7 centimeters, the length of the tube is 35 centimeters, and the dipole moment is 2.56, and the magnet's mass is 25 grams. And measuring the descent of the magnet, so we did 5 trials of the magnet falling through the tube, and then we took a recording of the time it took to fall, and an average of 1.52 seconds was concluded. And there's an image of us doing the experiments. For the computational model, we assume that the voltages in each segment of the tube are independent, so that way we could represent them as many small loops, and that the magnet stays perfectly centered in the middle of the tube. And so for this computational model, we broke the tube into many small consecutive rings, like we said in the last assumption, and we computed the magnetic flux and current in each ring, as well as the opposing force on the magnet. That'll be from this. And here are the results of the computational model. As you can see, we got 1.166 seconds, which is a little less than what we initially got in the experiment, but that will be talked about later why that differentiation could happen. And then some questions. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and which corresponds to counterclockwise current? And we said blue is clockwise because the current flows clockwise to oppose the change in magnetic flux, which is derived from Lenz's law, because the nature wants to stop change. And then what happens to the dynamics of the system when you flip the magnet around? All the currents, magnetic fields, and electric fields are going to be reversed, but have the exact same magnitudes as we calculated before. And then how does the total time in the tube of your real world system compare to that of your computational system? How might this computational system be made more accurate? And we found that it's slightly longer in real life, but this is likely due to the external magnetic fields and the unstable positioning of the tube. Because in the computational model, we assume that the positioning in the tube was at the center the entire time, but that's not how it is in reality. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar? And that we concluded it quickly reaches zero magnitude, which is equilibrium. And what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The current in the tube would increase quickly if we did this, which increases the opposing magnetic field on the magnet, or the magnetic force on the magnet, and it reaches equilibrium at a much lower velocity. And what if the holes or slots were cut in the tube? How would this affect the ring's currents in your model? And cutting slots would likely decrease the currents in the tube, which decreases the opposing force on the magnet. And some potential sources of error here are inaccurate measurements because we were recording it like with our finger. So being off by 0.2 seconds or something like that is very plausible. And an unstable position of the magnet tube, which we talked about in the previous questions. Defects in aluminum foil because aluminum foil is not all the exact same. And external magnetic fields, such as my phone being nearby, recording the timer, something such as that. Thank you for listening to this.